Hey there, Ravens. Welcome back. All right, part four and the final part. Actually turned into five parts now, didn't it? Okay, these are the named groups focusing on the non-metals. There are just two here. The first one is extremely important. These are the halogens. They're in group 17 or group 7A. They are very reactive. Okay? They have 7 electrons in their outer shell. They form what we call -1 ions, and they form salts with metals. Okay, hence the term halogen. Halo refers to salt. So salts are formed with metals, and salts are a specific, unique kind of ionic compound. All right, let's move on. Watch the video. It tells us a lot more.
The halogens form the seventh group in the periodic table, located just before the inert noble gases. The halogens are the most toxic and reactive of the non-metal elements. Each halogen has a distinctive color, getting darker as you move down the group. They are also poor conductors and have low melting and boiling points. Fluorine is a highly toxic, pale yellow gas. It is the most electronegative and reactive of all the elements in the periodic table, and can even form compounds with the noble gases. Because of its immense reactivity, it is difficult to isolate and store in its pure form. Chlorine is a yellowish-green gas that combines with nearly all elements. We use chlorine's high water solubility to our advantage by adding it to drinking water to kill harmful bacteria. Bromine is the only non-metallic element that is a liquid at room temperature. It is isolated from seawater for industrial use. It is a brown, noxious, and heavy liquid that is highly corrosive to human flesh, causing sores when exposed to skin. Iodine is a shiny bluish-black solid. Heating iodine to just over room temperature causes it to spontaneously sublime, meaning that it changes directly from a solid into a gas. Iodine readily reacts with most elements in the periodic table, but it will be displaced from its compounds by any of the lighter and more reactive halogens. Astatine is the only radioactive element of the halogen group. The longest half-life recorded for this element is just over 8 hours. Astatine has a metallic appearance and is semi-metallic in nature. The halogens are typical nonmetals with relatively low melting and boiling points. The melting and boiling points increase steadily going down the group. Fluorine and chlorine are gases at room temperature. Bromine is a reddish-brown liquid. And iodine and astatine are solids. Halogens readily combine with hydrogen to form hydrogen halides. These covalent compounds quickly dissolve in water to form extremely strong acids. Hydrogen fluoride is used to strip solid gold from circuit boards. The human body uses the super strength of hydrochloric acid to break down anything in the stomach. Looking at the periodic table can help explain the reactivity of the halogens. Here, the elements are listed in order of their atomic number, which represents the number of protons in an element's new number of electrons. And as the atomic number increases, so does the size and mass of the atoms. In the periodic table, each horizontal line is called a period, and it represents the number of electron shells normally possessed by the element's atoms. For example, there are 4 electron shells in an atom of bromine, so it lies in period 4. Meanwhile, an atom of astatine in period 6 has 6 electron shells. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. Astatine, with an atomic number of 85, is the only radioactive element in the group. Halogen comes from the ancient Greek halo, meaning salt, and genus, meaning former. Minerals containing chlorine and bromine are found naturally in rock and sea salt. The halogens all have 7 valence electrons, so all the elements in the group have similar chemical properties. Almost all atoms need 8 electrons in their valence shell to be stable. Because they only need 1 more electron to have a complete valence shell, the halogens are extremely electronegative and very reactive. As you move down the group from fluorine to astatine, each element is less reactive than the one before it. This occurs because the attractive force of the positive nucleus becomes weaker as it is blocked by an increasing number of electron shells.
Okay, and on to, pardon me, our last group of named compounds or named elements, and these are the noble gases, group 18, and they're noble because they're unreactive. Like nobility doesn't interact with the common people. They are unreactive because they have 8 electrons in their outer shell. They are also all gases. Let's watch the video.
The noble gases are the most stable group of elements. They are all colorless and odorless. With a few exceptions, they are inert, meaning they do not readily react with other elements. Helium is the second most abundant element in the universe, but it is rare on Earth. Because it is so light, it easily escapes the atmosphere. Most earthbound helium is in natural gas deposits deep underground. Neon is best known for the colorful lights of Broadway and Las Vegas. Not known to form any compounds, neon is completely inert. Argon is the third most abundant gas in the Earth's atmosphere. It is often employed to create inert environments for industrial processes and light bulbs. Krypton is occasionally combined with argon to create unreactive atmospheres for industrial processes. It is also used for lighting in high-speed photography. In 1962, scientists were able to form a compound between xenon and fluorine, making xenon the first noble gas to react with another element, and proving that even the noble gases can form compounds under the right conditions. It is most commonly used in high-powered and strobe lights. Radon is the only radioactive noble gas. It was first observed as a decay product of radium. It may present a health hazard if it is found inside a house. To understand why it is so difficult for the noble gases to form compounds, let's take a closer look at the periodic table. The elements are listed in the order of their atomic number, which represents the number of protons in an element's nucleus. In its ground or normal state, the nucleus is surrounded by a number of electrons equal to the number of protons. As the atomic number increases, generally so does the size and mass of the atoms. Reading from top to bottom, each horizontal line on the table is called a period. Each period represents the number of electron shells normally occupied by an element's atoms. For example, a krypton atom has 4 electron shells, so krypton lies in period 4. Meanwhile, a radon atom, in period 6, has 6 electron shells. Reading across the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. All of them, including radon, are radioactive. All the noble gases reside in group 18 because each one has a full valence shell. A helium full shell has 2 electrons. All the other noble gases have 8 electrons in their outermost shell. Because the noble gases need no electrons to be stable, they rarely react with other elements. Only the heavier noble gases form compounds, and then only in special laboratory conditions. Krypton, xenon, and radon will react because as you move down the group, an atom's hold on its valence electrons becomes weaker. The stability of the noble gases is actually a useful property. These gases are used in many situations where an unreactive gas is needed to maintain a safe and constant environment. Industrial processes such as welding rely on atmospheres of noble gases to prevent explosions, and vintners use argon to prevent wine from turning to vinegar. All of the noble gases will conduct electricity. Neon may be the most familiar gas used for lighting, but argon, krypton, and xenon also fluoresce, and combined, they create many different colors.
Okay, so noble gases are pretty cool. I like them in the way they fluoresce. Alright, and we've had enough of the same video series, so for fun, let's watch some elemental funkiness.
In 1869, Dmitri Mendeleev could see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythmic pattern that can form a funky beat. The elements we know about, they number 114. Some in quantities so small that they've never been seen. Most are common elements that are far and wide dispersed, but all of them together make up all the universe. Elements in group 1 are called the alkalis. They explode in water and are of very tiny size. They love to lose electrons when they form a bond. Of these reactive atoms, I can say I'm rather fond. Group 2 elements are often called alkaline earth. Calcium's been building bones since well before your birth. They form nice +2 ions and are generally quite fun, though they're not quite as reactive as the metals in group 1. Since 1869, every one of us could see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythmic pattern that can form a funky beat. Metals in groups 3 through 12 transition elements. Some of them are lightweight and others really dense. Things they have in common, they form charges 2 or more. And some form colored compounds, which is something we adore. If you want an element, just tell me once again. If it's in group 17, you've got a halogen. Non-metals so corrosive, they're not found in their pure state. They can gain electrons like they're going out of date. Got one for you in group 18, it's known as noble gas. If you're looking for an element that just sits there on its... If you wonder why and haven't figured it out yet, their valence configuration is a big stable octet. So now it should be obvious that everyone should see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythmic pattern that can form a funky beat.
Nice way to end.